Hello, in this video we will generate the dataset of the arcsine function and the Taylor-Maclaurin series sum expansion. First, we begin with the arcsine function. Array formula, arcsine of the x values. And we'll chart this. Insert chart, and we'll use scatter chart and show the trendline equation. Here we will use the polynomial and we'll raise it to the power 6. We show the equation as label and polynomial raised to the power 6. And we'll also move to the left for comparison. Move the polynomial equation to the left for comparison purposes. Now that we have the polynomial, we enter the expansion, the Taylor-Maclaurin series sum expansion, which is equal to the summation of a times x to the power 2n plus 1, where coefficient of a is equal to 2n factorial divided by 4 to the power n times n factorial squared times 2n plus 1, where the values of n start from 0 to infinity. In this case, we can only reach the limits within our data set. This approximation can be limited to 10, values of 10. Now we can enter the Taylor-Maclaurin series expansion of arcsine, which is array formula of series sum x values, where the values of x is 2 to the power n, starting from 2 to the 0. 2 times 0 plus 1, that's 2. So that is 1. That's the beginning. Followed by, what's the increment? So 2 times 1, 2 times 0 plus 1 is 1. 2 times 1 equals 2 plus 1, 3. 2 times 2, 4. So then it will be 1, 3, 5, 7, 9, 11. So there's an increment of 2. And the coefficient will be this range. Now we start working on the coefficient, beginning with the numerator. Array formula, that's 2n factorial of 2n. So 2 times n. So that's a factorial of 2n. Next, we work on the denominator. So that's the numerator. So the denominator will contain 3 parts. Let's enter the first part, which is 4 to the power n. So that's 4 to the power n. And this is n. Enter. The second part of the denominator. The second part is n factorial squared. So times factorial to the power 2 and the factorial of what? N. We're getting closer. But let's enter the trend line here because there is no trend line on There's no trend line. So we add a trend line that's polynomial to the power 6. So we're getting closer. The third part and last part. So we have the first two of the denominator. The third part will be 2n plus 1. So we multiply. This is the denominator. You can go inside the denominator times 2n plus 1. 2 times n plus 1. Now they are all in the same line, but we still don't have the equation. So let's edit the chart, go for series. Why is there no equation? Because we did not show the equation, use the equation. Let's compare the regression coefficients of the trend line. B1 is B0 is 0, B1 is 1.15, 1.05. B2 is 0, 0. B3 is negative 0.732, negative 0.182. So there's, as the degree goes higher, there's already a difference. And the trend line, they're only accurate up to this portion. Beyond that, there's already a difference between the two, but they are the same here in this area. We will calculate this regression coefficient using Linus. Let's begin with the arcsine function. To do that, we have to complete the 1 comma x matrix, where this column is x to the 0, x1, x squared, x cubed until x to the 6. So we enter the power transpose, and this will be from 0 to 6. Now we can complete the 1 comma x matrix, which is RA formula of these values, the x values. Oh, no, this should be RA formula of the x values to the power of these values, and enter. Now that we have the 1 comma x matrix, we can use the line nest, starting with the arcsine. R line nest data y and data x. And we enter the line nest also for the expansion, which is line nest data y and data x. So b0, they are 0. That's b0, matches to our trendline equation. B1, 1.15, 1.05, also a match. B2, they're all 0. B3, there's a bit of difference, but they match to our trendline equation. B4, they're both 0. B5, 0.108 in this part, 0.522, and B6 are all 0. Our A1 is almost equal to B1. This is A0. A1 is 0.166. So there's a difference here in the trend line. The expansion coefficient does not match to the regression coefficient, but our trend line shows that they are a good match. This completes the Taylor-Maclaurin series sum of the arcsine function and its Linus polynomial